Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. Today it's my pleasure to welcome Chad Mirkin, Professor and Director of the International Institute for Nanotechnology at Northwestern University. Chad is one of the few scientists to be elected to all three U.S. national academies, medicine, science, and engineering. Chad is a well-known nanoscientist. He is also the founder of several companies which are actively commercializing nanotechnology applications in the life science and semiconductor industries. Chad, thank you so much for being with us today. To get things started, could you tell us a little bit about yourself and how you first got involved in nanotechnology?
Sure. I started out as a chemist. I was trained as a synthetic organometallic chemist at Penn State. Moved to MIT to do a postdoc where I learned a little bit about surface science and electrochemistry. Worked for a really famous guy at the time, a guy named Mark Wrighton, who was interested in the consequences of miniaturization. He was a little bit ahead of his time. At that time, we were looking at microscale systems, and I was pretty much at the right place at the right time with the nanotech revolution when I started my independent career at Northwestern University. And it was clear that there was tremendous interest in first miniaturized chemical systems at the time, but this idea that matter behaves very differently when you shrink it down to the sub-100 nanometer length scale. And the first tools for manipulating matter on that scale were becoming commercial, things like atomic force microscopes, scanning tunneling microscopes. And I thought I should go learn how to use some of these tools. And I went to a facility and effectively self-taught myself how to use an AFM. And pretty soon we were developing all sorts of new capabilities based upon these tools and thinking about developing the modern field of nanoscience through primarily chemistry-driven approaches.
So you mentioned developing capabilities, and you've developed nanoparticle-based biodiagnostics and therapeutic tools. How does nanotechnology play a role in enabling these technologies?
Well, look, nanotech, I think, is important for many technologies. We've really had a major focus on biomedical, but anywhere where new materials are important, nanotech's going to play a role. And the reason I say that is everything old becomes new when shrunk to the sub-100 nanometer length scale. Any material that you have, if you shrink it down to this scale, it takes on new properties. And a lot of the science is about figuring out what those properties are and how they relate to the particular structure that you have. But the applications are driven by those new properties that you discover. And in the area of biodiagnostics, we learned very early on that when you take gold nanoparticles and decorate them with oligonucleotide strands at high density, you create a new structure that we now refer to as a spherical nucleic acid structure. It has really unusual properties that are very different from the linear nucleic acids from which it derives, different from, in fact, even the gold particle core alone. And one of those is the ability to bind to complementary targets with very high affinity. And so that property becomes the basis for very sensitive labels for different nucleic acid signatures of disease. We quickly developed a whole series of new assays based upon these types of particles as probes that soon became commercial assays. And in fact, the Verigene system that's sold by Luminex, which is for point-of-care medical diagnostics, is now in half the world's top hospitals and used quite heavily for disease diagnosis.
Could you share some exciting developments over the past 20 years or where you have seen your work build upon itself and evolve into new areas?
So that's a great question because we just had a really big discovery that was reported in Science literally last week. If you go back 2 decades ago, our lab's fairly well known for inventing what we like to refer to as the world's smallest pen. At the time, which was 1999, we discovered that you could use an atomic force microscope to locally control chemistry between tip and surface, taking advantage of what many people in the field viewed as a problem, but we turned into a major plus, which was water collects at the point of contact between tip and surface, and that water sucks the tip down and convolutes any sort of measurement you make thereafter. If you think about water as a solvent that's involved in a chemical reaction, you can begin to use it to your advantage to pattern materials on a surface with the resolution of an AFM, hence the world's smallest pen. Over the course of the next decade, we actually developed it into a tool that used up to hundreds of thousands of pens to pattern in parallel. And then we even commercialized many of those instruments, and those are used for research purposes all around the world. in many different research labs, both in universities and in industry. Very recently, literally last week, we reported a really exciting discovery, and that was that you could go from really tiny structures using many of these concepts to really large structures. And in fact, we reported the world's largest and fastest 3D printer for printing polymer-based materials. We can, over the course of a couple of hours, print something the size of a human being from almost any sort of polymeric resin. That turns out to be not just interesting, not just a kind of gimmicky type of capability, but could be a game changer in the way we think about 3D printing. Could move the field from prototyping to manufacturing. And others have tried to do this, but nobody has had the throughput and speed that we've reported. And that throughput and speed and materials generality turn out to be the enabler. So instead of having warehouses of parts, you literally simply need a barrel of resin along with these printers, and you can print on demand anything you'd like, ranging from things like Invisalign, orthotics, the soles of tennis shoes, medical parts, parts to cars, parts to airplanes, even materials that can be used in construction. And so we're finding that, again, this focus initially on making really tiny structures, and then ultimately this ability to span 18 orders of magnitude in terms of dimension is really quite the game changer.
So first, about your institute. When you pulled together the International Institute for Nanotechnology, which, if I recall, predates the formation of the NNI, you brought together chemists, engineers, biologists, physicians, and business experts from across the university. Can you share a little bit about what the thinking was in standing up this institute and what you've seen over the years since it's been established?
Well, as I said, I was really quite fortunate in terms of timing. So in the 90s, we were thinking about building another wing of chemistry at Northwestern, and we had to raise money to build that wing. And we talked to a lot of the folks that were going to help in that regard, and they wanted a theme to focus on. And we at first thought we'd go after genomics, and many people said, well, that's nice, but that's been done before. That's just not that exciting. And in thinking about some of the things that were going on at the time, we realized that we had a common focus, and that was that many people were interested in miniaturized systems and how there were chemical consequences associated with miniaturization. And so we thought, why not build a center focused on this idea of nanochemistry or nanotechnology? And then we realized that, hey, we should not just focus on chemistry. We should use this as a way to bring together people from many different disciplines that could broadly look at the consequences of miniaturization, regardless of their field of interest, whether it's physics, biology, chemistry, or any form of engineering, and eventually medicine. But when we started it, I realized that this was going to be a really spectacular way of doing science and a way of rapidly making advances in many fields, following the general tenet in nanotechnology, which is that everything when miniaturized is different. But I also realized that if we were going to build an institute that was going to attract additional support and resources and interest, we had to focus not just on the science, but also on the technological output. And so I thought it very important to begin to form bridges with the business school, for example, at Northwestern Kellogg, so that they could help the scientists who made interesting discoveries, discover new materials, new processes that had translatable capabilities. They could help them write business plans and ultimately attract investment that would give them a shot on goal to develop technologies that could impact the masses. We did that with my first company, Nanosphere, and that was an interesting exercise. One, as it worked, it ended up developing powerful new medical diagnostic tools based upon gold nanoparticle spherical nucleic acid technology. But it was actually the first company at Northwestern that was ever started through Northwestern Science that ended up becoming a public entity. So that company went from startup and an employee base of one to hundreds of employees, ultimately a NASDAQ-traded company, and then one that was acquired by Luminex. And that really got us up and running. Since then, we've started over 20 companies, raised over $1 billion worth of venture capital and related investment, and have created a machine that gives scientists within the Institute a chance to take their discoveries and translate them into technologies that can impact the masses.
I've heard you in the past talk about the importance of tools and infrastructure. In fact, I think I've heard you say, if you build it, they will come. With respect to international competition in the area of nanotechnology and the research infrastructure that's required to do this type of work. Could you comment on your observations with respect to the NNI and the infrastructure that's been developed under this broad initiative?
Look, I think it's a lot like building any great organization. You want to have the best infrastructure in terms of buildings to do the research. You want to have the best instrumentation, because instrumentation drives new science. All of the powerful microscopes that have been developed in the modern age of nanotechnology are driving many of the most important discoveries. New materials and new techniques drive the field. And so we thought it was very important to become world class in terms of the facilities and instrumentation, and that would ultimately create a magnet to draw all of the talent in the world to Northwestern. And that turns out to have paid off. A great example of that, of course, was moving Fraser Stoddard from UCLA to Northwestern. And then, of course, he wins a Nobel Prize for much of his work related to nanotechnology. But he's just one example. We've had so many great people come and join us at the Institute. People like Will Dichtel from Cornell, Sam Stoop from Illinois, Neil Kelleher, John Rogers most recently. And then when you get those types of people to come and join you, you get the best students and postdocs that want to do the research in this field. And so this has been a very interesting exercise and frankly, a very good bet made by the university. And I think a very good investment made by many of the agencies that have supported it over the last 15 years.
We've hit a little bit on interdisciplinarity. Can you comment on your perspective on how people have approached interdisciplinarity over the past 20 years? I remember when it was taboo to speak across engineering disciplines, let alone into chemistry and physics and biology. What have been your observations?
I think nanotechnology has been one of the greatest gifts to science, not just because it was a grand opportunity to discover new materials and new capabilities in science, but it changed the way we do science. If you do nanotechnology research properly, you realize you can't do it alone. You realize that you need a group of different types of individuals to do it properly. Within the Institute, we like to think of what we put together as one giant bullpen of talent at the faculty level and at the student level. And so the students know within the Institute, if they're working on a core problem in chemistry or in physics or in biology, they can cross disciplines, they can find experts within the Institute to help them move into areas where they might not feel like that's their strongest suit, but they can still pursue and make important advances across the boundaries of disciplines. They know that if they have some great experimental work, they can couple it quickly with theoretical work and simulations with many of the great theoreticians that we've put together that span many disciplines like chemistry, physics, and different forms of engineering. And so I think one of the really nice things that we've seen happen over the last couple of decades is this idea that we should have fiefdoms, where you build walls around what you do and try to be the best at that and not allow anybody else in, to really open up and realize that you can get a lot more done by working together. It's a much more efficient way of doing science, but it's also a better way of doing science. You can get a higher quality answer by merging the capabilities and expertise from people both within your discipline and also outside of your discipline.
So, as you know, the NNI is celebrating the 15-year anniversary of the signing of the 21st Century Nanotechnology R&D Act. And this podcast is really part of wrapping up the year of looking back and looking forward regarding what the NNI has enabled. You sit at I think, a very unique position, not only as a researcher and an entrepreneur, but as a leader of several of the NNI studies and also a member of PCAST that provided a review of the NNI not too long ago. So from your perspective, can you share your thoughts on the NNI, maybe looking back over the past 15 years and then looking to the future?
Well, I think the NNI was really quite important and still is important. I think it puts a spotlight on a very important field, one that we must stay competitive in. If you travel around the world, and I do a lot of traveling, you realize that other countries, including China, Singapore, and many countries throughout Europe, are doubling down on nanotechnology. They're being really quite smart about this. The U.S. was smart because they were first, and it's critical that we realize we build a very strong infrastructure, but we have to build off that infrastructure and capitalize on it. So the first lesson is that we're just getting started. The idea that you have something as big as nanotech and you have a relatively short period of time, 15 years in this case, and that you've done all the hard work and now it's time to move on, is, I think, a very silly one, especially when you think about the fact that nanotech's unique. It's not based upon a particular subfield. It's not based upon a particular type of material or type of technique. It's about redefining much of what we call science and engineering and now aspects of medicine. So I think the critical observation is that it put a spotlight on an area where there could be rapid scientific discoveries. It put a spotlight on an area where we could see many of those discoveries make a difference in terms of developing technologies that can broadly impact the world, whether we're talking about medicine, whether we're talking about energy, whether we're talking about the environment. And I think we have to think about how we move forward and best plan our strategy to capitalize over the next 30 years, because this is a field that's going to be around for a long time.
So I think that one of the most exciting attributes of nanotechnology from my perspective, what makes my job very exciting and interesting and different every day, is the fact that nanotechnology impacts all of these other areas and has become a way to approach science for a wide variety of applications, which also makes it challenging to explain maybe what's been accomplished or what is possible in the future. Can you share your thoughts on communicating successes and opportunities?
Well, look, I think we've had an enormous number of successes. The microelectronics industry is now a nanoelectronics industry. In the area of medicine, we now have diagnostic tools that are used all over the world to diagnose disease, to treat disease, to track disease in unique ways. We have powerful new therapeutics that are going through clinical trials. As you move from science to technology and from technologies that are relatively simple and have low hurdles in terms of regulatory issues to ones that have higher hurdles in terms of regulatory issues like medicine, the timeline has to expand. And that's true of nanotech or non-nanotech type applications. One of the things that I find frustrating is somebody will say, well, why don't we have all sorts of new therapies that are based upon nanotechnology that are changing our lives? Well, those are coming. It's just the timeline of development is not the 10, 15-year timeline. It's the 20 to 30-year timeline. And that's simply because you have to go through a lot more testing to get those technologies ultimately approved. We have dozens of drugs now that are in clinical trials based upon nanotechnologies and nanoformulations. Many of those, I think, are poised to completely change the way medicine is practiced, the way we treat disease, including many forms of cancer. And early signs are actually quite good in that regard. In the area of energy, we're beginning to see lots of new materials make a difference there. In the areas of the environment, the development of new types of detectors, new ways of cleaning up water, new ways of cleaning up the air, many of them are coming from nanoengineering approaches. So I think that the future is pretty bright in this regard. I don't think we have to be apologetic for what's been produced to date. In our own case, we have over 2,000 products, commercial products that are sold today that have a link to advances within the Institute. And that's a large number of I think, a technological product output.
So I want to ask you a question from the point of view as a mentor. And we facilitate a network of undergraduate student groups and try to provide them opportunities that they might not have and to learn from each other. If an undergraduate came to you and was just getting started and asked for advice with respect to future opportunities, what would you tell them?
In nanotechnology?
Yes.
Yeah, it happens every day. I've had over 100 undergraduates do research in our labs, in my personal labs at Northwestern over the last 20 years. I think it's an incredible land of opportunity. And the reason is very simple. First, within this area, we teach you how to do science properly, how to break down a problem, how to solve a problem. regardless of your core expertise. And I think that's an important observation. So we teach people to go find complementary expertise that allows them to be better in terms of trying to solve the problem that they're focusing on. The second is we try to train people to not just do science, but to think about what I could do if I actually solve that particular problem. What does that new information allow me to do? What does that new structure, new material allow me to do that I couldn't do before? This way of doing science, engineering, and medicine under the nanotechnology umbrella, I think, is an incredible training ground and one that prepares young people to pursue careers that I think will be very rewarding for them, regardless of their subdiscipline of interest. The neat thing about this is you can be primarily a chemist or primarily a physicist or primarily a biologist and be a nanotechnologist. You just learn how to work with the other groups to make sure that you have all of the capabilities you need to solve the problems that you're trying to address.
Well, I think that's great advice, and I want to thank you so much for taking the time to talk with us today. Do you have any closing thoughts that you would like to share with our listeners?
Look, I think first and foremost, science is one of the greatest areas to pursue a career in. I've never second-guessed my choice to become a scientist. I've never second-guessed my choice to become a nanotechnologist. It's a tremendous gift to be able to come to work and try to discover things people haven't discovered before, explain things people didn't understand before, and then in our case, to be able to take those discoveries and translate them into products that can have a positive impact on humanity. So you're young, energetic, and interested in science, I strongly recommend that you explore a career in nanotechnology.
Thank you for joining us today for this special 15-year anniversary edition of Stories from the NNI. For more stories, subscribe wherever you get your podcasts. If you would like to learn more about nanotechnology, please visit nano.gov or email us at info@nnco.nano.gov.